Friends, today we will have the 7th lecture under the NPTEL course on offshore structures under special loads including fire resistance. Today in this lecture we will talk about one of the new generation platforms which is recently conceived, which is offshore Triceratops. We have already said that in deep waters compliant structures are successful, but there were some limitations. We also agree that oil and gas reserve is moved towards ultra deep waters. We also agree that under these deep and ultra deep waters, the environmental loads caused by waves, wind, current, etc., though they are conventional, but they are more severe. Hence, a structural geometry or a structural form which resists loads by large displacement of rigid body motion is now not preferred. We do not want preferably the deck to remain isolated from the support system. Hence, one can say now the geometric form of offshore platforms need special attention in terms of its design. There are different types of new generation platforms which are conceived for ultra deep waters. Foremost idea which came into mind is from buoyant leg structures. Essentially, they have the top side as similar to a drilling platform with a multi-tier hull, where the drilling derrick is located and drilling is enabled through the derrick. There are other facilities like a flare boom, a heli deck, a living quarters, etc., which are present. Now, the support system is very interesting in this case. Let us say the support system can resist the lateral loads through the spud can arrangement. The tower should be now supported with additional buoyancy modules So, these are buoyancy modules. So, the connectivity between the modules is what we call the cone arrangement. This is called as the upper stem, and this is of course called as the lower stem. So, in general we call this as buoyant leg, therefore, buoyant legs are actually similar to tethered spars, they can sometimes also have group of cylinders connected together. They are seem to be attractive form compared to TLPs and spar platforms. They are better. They are essentially positive buoyant, where one can say buoyancy very much exceeds the weight of the structure. They also have a positive metacentric height by design. Which enables a better structural stability. So, essentially buoyant leg structures do not derive stability support from tethers. So, the idea of TLPs supported by tethers or tendons becoming integral part of the weight distribution system is now replaced by less significant role of tendons in stability. So, essential features of any buoyant leg system: 1, a deep draft system; 2, high stability; 2 characteristics makes it insensitive to ultra deep waters. So, by design it may be preferable. Let us now look into the construction aspect. We already know for deep waters 2 effective conceived structural forms were TLPs and spar platforms. So, installation process of a buoyant leg structure is similar to, or rather we can say a combination of both TLP and the spar. So, pre-tension in support systems like tethers or imposed by either ballasting or by pull down, or sometimes both by ballasting and pull down. Please look at the screen. These are different forms of buoyancy chambers which are generally used as buoyant towers, which comprises a buoyant leg structure. You can look into the large diameter towers which are essentially used as buoyancy chambers in a given system, which actually supports the deck and then further connected to the seabed either by a mooring system or by a TLP similar to a tendon system. Extending this philosophy, offshore engineers innovated a new structural form called Triceratops. A typical Triceratops conceived in the beginning of an idea consists of a deck with all topside details, with the buoyant legs, three set of buoyant legs, the seabed is somewhere here. These buoyant legs, one end is connected to the seabed using a tether or a tendon. So, these are tendons. Similar to that of a TLP, they will be in axial tension. The other end of these buoyant legs was connected to the deck with the help of a ball joint. So, essentially joints isolate the deck from the buoyant legs. So, buoyant legs are free to move or to respond under waves, because this is going to be my water line. So, they can rotate and they can displace. However, it is interesting that the rotation of the buoyant legs will not be transferred to the deck, because the ball joints will observe these rotations. So, one can say that ball joints transfer all translations from the buoyant leg to the deck under wave action, or vice versa under wind loads. They do not transfer moment about any axis, that is no rotation transfer. So, this makes Triceratops an unique structure. One can say it is deck isolated platforms. There is a great advantage of transfer of displacement degrees. For example, heave motion is transferred from the buoyant leg to the deck. This ensures a rigid body motion in vertical plane, which is required for any complaint system. So, this is similar to any complaint structure like a TLP. Therefore, ball joints restrain transfer of rotation from buoyant leg to the deck, but allows transfer of displacement from buoyant leg to deck. So, obviously, if you have the deck on its CG, the system may have 3 degrees of freedom, that is surge, sway and heave. Whereas, the buoyant legs with the ball joint will have 6 degrees of freedom measured at the local CG of each buoyant leg. Now, why each buoyant leg will be independent? Each buoyant leg has a freedom, is free to respond to waves. So, the total system will have 9 degrees of freedom. Translations are transferred. In fact, I should say interchanged or exchanged between deck and legs. Rotations are restrained. By having such a form, what are the advantages? One can expect a large reduction of forces exerted on the platform deck as a transfer of force from the substructure, because we all know deck is not directly exposed to wave action. In this case, substructure is buoyant leg. However, when the deck is exposed to wind loads, there is a direct action. Secondly, the buoyant legs also allow risers to pass through. So, risers are now protected from lateral loads, which was not the case in TLPs. Risers were exposed to lateral loads in TLP. Therefore, the riser deck coupled response was more critical in TLPs. Of course, this problem was solved, was addressed in spar platforms, because in spar platforms risers are made to pass through the deep draft cylinders, and risers are partially protected from wave action. So, main advantage is also derived from the presence of ball joint. The system now derives all advantages of a TLP, be positive buoyant, that is buoyancy force exceeds the weight by a large amount, remains afloat in case of failure of tendons. Therefore, safety of the platform asset is ensured even under critical accidents. Easy and fast installation, less downtime, convenient decommissioning is also important. It also derives a few advantages from spar. A deep draft caisson ensuring good stability, slow and steady recentering capability, stability even under failure of tendons. In addition to this, it derives one major advantage due to the presence of ball joint, that is deck is isolated from the support system. Therefore, deck and support system do not respond one simultaneously, at least in rotational degrees of freedom. 2. deck response is expected to be lower compared to the supports because of isolation. So, some of the classical advantages are derived because of presence of ball joint alone. It derives one important disadvantage which was also present in spar, actually due to deep draft buoyant legs. It is expected to undergo severe corrosion. So, that can be a very severe demerit which is unusual in case of deep water platforms. Now, friends, I would like to show you a very interesting case study which has been carried out at IIT Madras on this new conceived idea, which I will discuss in detail using experimental investigations. Please pay attention to the presentation now on the slide. We all agree that deep water platforms and ultra deep structures can be, with the help of TLPs, with the help of spar platforms, semi-submersibles, buoyant leg structures and Triceratops. Triceratops is relatively new concept suggested for deep water oil exploration. It consists of a deck structure, 3 buoyant legs, ball joints connected between the deck and buoyant leg, and a restraining system similar to that of a tension leg platform, and of course, a foundation system. Please pay attention to the figure shown on the screen. Triceratops is a conventional idea conceived by White et al. In 2000 consists of a deck with all topside facilities. The ball joint is present between the deck and the buoyant legs. Usually buoyant legs not a single cylinder, it is a set of 3, 5, 7 cylinders which are interconnected. However, each leg stay in isolation, they are not interconnected. Therefore, each set of legs have freedom to respond to the wave action independent of the influence of other legs on the deck. So, ball joints transfer only translational motion, but no rotation. So, there are specific advantages derived from Triceratops geometry, better motion characteristics, wells are protected within the buoyant legs and they are laterally supported, relatively a simple form of geometry, good station keeping procedures, easy to install and decommission the platform, highly reusable and relocated, simple restraining system, does not require a high tether tension as in the case of tension leg platforms, very highly stable because positively buoyant system, relatively low cost because installation and decommissioning is very fast with the lowest possible downtime. It is a positive buoyant system, therefore, resembles spar due to deep draft and motions are more or less similar to that of a tension leg platform. So, it derives advantage of both set of deep water platforms, namely tension leg platform and the spar platform. A typical study which has been conducted to compare the preliminary analytical studies results are shown here. If one can look at the experimental investigation conducted by Shever et al. And then the present analytical model what we investigated at IIT Madras for a single buoyant leg structure, the periods are really very high in terms of surge and sway degrees of freedom, making it highly compliant, whereas in case of heave, roll and pitch the periods are very close. However, they are still higher compared to that of conventional TLPs. So, buoyant leg structure alone as a single standing system is unable to support the exploratory process because of very high roll and pitch degrees of freedom. So, it is effective that we have to attach the buoyant leg to the deck using some unconventional or a special kind of structural member which isolates the deck from that of the buoyant leg. So, now the ball joints are placed in between the buoyant leg and the multi-tier deck as an experimental model, and now for the experimental model one can compare the tethered and free floating analysis and for the values given on the screen now for its geometric property on a scale of a model at 1:150, which is investigated experimentally at a water depth of 600 meter for a specific prototype, whereas in the model study a relative scale has been adopted. The principal particulars of this particular model, which has been investigated on two issues, floating and tethered for the same water depth for a more or less a similar draft. The particulars of each buoyant leg in terms of the buoyant legs, the deck and the pretension are available on the screen now. The classical equation of motion for a free flow vibration study will help us to find out the free periods which are seen on the experimental model. One can see here for a free floating system the experimental models show the heave and roll pitch degrees as you see here, whereas for tethered Triceratops they are showing slightly a very high value compared to TLP. However, they have a very strong heave restraint system. So, the platform is heave restrained in vertical plane, whereas the platform remains isolated and very highly compliant in horizontal plane, that is in surgeon sway degrees of motion. So, we have seen that Triceratops derive advantages of a TLP and a spar. Spar because deep draft system, TLP because tendon supported substructure. In addition, it derives an advantage because of the ball joint. So, the natural periods are more or less similar to that of a TLP in horizontal plane, ensures the desired compliancy, it is stiff in vertical plane by restricting the heave motion. Therefore, without compromising the operational advantages, the structural form is conceived which is highly novel. In the next lecture, we will show you some of the results of Triceratops under wave and wind action as a sample study which we conducted. We will also talk about one more platform which is used for LNG exploration in the next lecture. So, friends, in this lecture we spoke about a classical new generation platform which is a conceived idea in the recent past, which is Triceratops. We have seen the advantages derived from the existing structural forms to conceive a new structural form for a Triceratops. We have also seen and understood now, realized the advantage of placing a ball joint and isolating the deck from the substructure, because the deck isolation enables the deck and the substructure to behave independently on certain degrees of freedom which are translational, which are transferred, but rotational degrees of freedom are not transferred. So, under rotational degrees of freedom like yaw motion, roll and pitch motion, buoyant legs do not transfer them to the deck, whereas on vertical plane, for example, the heave motion, or in horizontal plane, for example, the surge or sway motion, they are transferred, ensuring a rigid body connection. though it is an hybrid system, but the hybrid system is still far compliant with larger periods in horizontal plane and lower periods in the vertical plane. Thank you very much.